Let's look at a circuit where the we have two transmission lines that are connected together to transition, and you might ask yourself, what is the difference between this structure and the structure that we just got through analyzing? Everything appears to be the same as the circuit we just looked at. We have a transmission line of Z01 on one side and a transmission line of the characteristic impedance of Z02, a dissimilar characteristic impedance on the other. We have a transition, which we've indexed as Z is equal to 0. Z, the index, increases as we move from left to right. Everything looks the same. The one difference from what we, the structure that we analyzed prior, is that the second transmission line is terminated in a load that's numerically equal to the characteristic impedance. So this load is the, quote, match load for this transmission line characteristic impedance Z02. So that's the addition that we added on to the structure that we analyzed previously. Our expression for the total voltage and total current are precisely the same as before. And again, I emphasize these are valid only for index Z, which are non-positive, negative, or equal to 0. Along the second transmission line, again, we have a total voltage and total current that are dependent on the two unknown wave amplitudes for the second transmission line, V02 plus and V02 minus. Again, these are valid only for indexes Z, which are non-negative, 0 or greater than 0. And so what's the difference between this and what we did before? Well, again, it's this addition of a matched load at the end of this transmission line. Let's see how that affects these general solutions. Since the load terminating the second transmission line is numerically equal to its characteristic impedance, we know that's a special case wherein there is no reflected wave. In this case, the minus wave is equal to 0. And since the minus wave is equal to 0, it has no power, and therefore it manifests itself with respect to no current and no voltage. I minus and V minus are equal to 0 for this particular situation where the transmission line is terminated in a matched load. And so we can say that V2 minus, for example, is equal to 0. Because of that, the second term for each of the total voltage and total current for the second transmission line, the second term goes to 0. And so we have a solution for the right side of our circuit that's very much simplified from our original analysis that we accomplished prior. Because this load is a matched load, the total voltage and total current reduces to this single term solution. So let's then evaluate these voltages and current at our boundary, at the location index of Z equal to 0. For V1 and I1, we find that the results depend on both V plus and V minus. For the second transmission line on the right side, we find that the result depends only on V0 plus. And of course that makes sense because V0 minus on the second transmission line, V02 minus, is equal to 0 since our line is terminated in a matched load. Applying then the boundary conditions, we find that we have two expressions relating the wave amplitudes V01 plus and V01 minus, the wave amplitudes on the left side of the structure, to the single unknown wave amplitude V02 minus on the right side of the structure. And so we have two different equations, and this one includes also the characteristic impedances of our two transmission lines. We look at this and perhaps are a bit perplexed. We have two equations and we have three unknown wave amplitudes. So what do we make of these results? What can we use these results for? How can we use them to discern anything physical about the behavior of this circuit? we must stop and think about this math and try to relate it to the physical reality of the situation. So we have V01 plus, and that is the wave amplitude associated with the propagating wave on the left side of this interface, the wave that is propagating toward the interface. What about the other two unknown wave amplitudes? We have V01 minus, and that describes the wave that is propagating now from right to left, propagating away from the interface. The final unknown complex wave amplitude we have is V02 plus, that should be a 2 right there instead of a 1, V02 plus, which describes the plus going wave, the direction propagating in increasing z from left to right. And of course that wave is likewise propagating away from the interface. So for the three unknown wave amplitudes we have, one wave amplitude describes the wave propagating toward the interface, and the other two wave amplitudes, V1 minus and V2 plus, describe the waves that are propagating away from this interface. These two waves that are propagating away from the interface are waves that we describe as the scattered wave from that interface. And so we have a way of sort of separating our waves into two categories. There are the waves that are propagating toward this discontinuity, this interface, and then the waves that are propagating away. The waves propagating toward we call incident waves, and there are one in this case. Because we've terminated this transmission line in a matched load, there is no wave propagating toward the interface from this side. On the other hand, we have two waves propagating away from the interface, one moving left from the interface, or the transition, the other moving right from the transition or the interface. We call these two waves the scattered waves. And so we assign a causal effect here. This wave propagating toward the interface strikes the interface, and it creates two waves, one which bounces or reflects from the interface, that is V1 minus, and the other which transmits across the interface and becomes then V2 plus, propagating in this direction. And this is our physical interpretation of these results. This is our cause, and these two things are our results. And this is very reminiscent of what we had for a terminated transmission line, where we wrote the reflected wave in terms of the incident wave. Now we have two scattered waves that are a result of this incident wave. This is the source, the independent value. These are the dependent values, the dependent structures, mathematical descriptions that occur from this incident wave. Because of that, what we're going to seek to accomplish is to determine the value of the two, or the amplitudes, the wave amplitudes of the two scattered waves, V01 minus and V02 plus. Again, that should be a 2, in terms of the source, the independent value V01 plus. V1 plus propagates toward this interface, and we have two waves that scattered. We want to find the unknown wave amplitudes of these two waves in terms of the cause, in terms of this one wave amplitude of the single incident wave. So to accomplish this, we first insert our KVL expression into our KCL expression. And when we do that, this is V2 minus, or V2 plus rather, at this point, and we insert the KVL in there. We get an equation where we have two unknowns, and we rearrange that equation to determine the value of V01 minus. This is the wave amplitude of that minus, that reflected or scattered wave, in terms of V01 plus, which is the wave amplitude of the incident wave on that interface. And so we've expressed the scattered wave amplitude of V01 minus, the unknown, the result, in terms of the V01 plus, the cause that creates these two scattered waves. Now that we have an expression for V01 minus, we can insert that into our KVL equation, and now we have a relationship between the unknown wave amplitude V02 plus This is again the wave that's propagating away from the interface in the direction of increasing Z on the right side of our circuit in terms of the source, the incident wave V01 plus. And so we can conclude, when we put both of these results together, that the relationship, the ratio of V01 minus to V01 plus is equal to this, and the ratio of V02 plus to V01 plus is equal to this. And this is typically how we describe our results. In the numerator we have the dependent variable, and then in the denominator we have the independent variable, the source, the incident wave that creates these two scattered waves. And of course the ratio of these two things are a value that depends explicitly and completely and only on the physical description of the circuit. In this case, we really only have two parameters involved, and that is the characteristic impedance of the transmission line on the right side and the characteristic impedance of the transmission line on the left side. And so we find both of these results depend on those two values and those two values only, Z01 and Z02. And so from that standpoint, they pass the sanity check. We use these results then to determine an explicit expression for the minus wave voltage for the first transmission line. So this is the wave that's propagating back up the line in the direction of decreasing Z on the right side of that circuit in that first transmission line. And we see this result is dependent ultimately on V01 plus, which is the wave propagating down that first transmission line toward the transition, or that interface there. So this makes sense that the minus going wave depends on the wave amplitude of the incident wave and depends on the physical parameters of that structure. On the other side of the transmission line, on the second transmission line, where the index Z is greater than 0, again we insert the value for Z02 plus that we just calculated, and we find a result that is dependent on this independent variable V01 plus, the wave amplitude of the incident wave that is propagating down toward our interface. And we see that these two results are very different, and they should be, because this is the scattered voltage on the first transmission line, and this is the scattered voltage on the second. So we can go through and determine then the total voltage along the first transmission line and the total current along the first transmission line by simply adding together the plus wave voltage to the minus wave voltage, and likewise for the current. For the second transmission line, the total voltage and current are simply equal to that scattered wave voltage and current which we just determined. There's quite a bit of algebra that takes us from applying our boundary conditions and taking our telegrapher equation solutions and going through algebraically and finding the values of our wave amplitudes and inserting them back into our solutions for voltage and current. And of course there's much opportunity to make a mistake. The great thing about applying boundary conditions and finding the answer is that you can always check to see if you've done it correctly. You can always apply a sanity check, and I urge you to go through and do that. Anytime you go through the process and say, I'm trying to find the values of the wave amplitudes that will satisfy certain boundary conditions, once you find those values, insert them back into your solutions and see if in fact they do satisfy your boundary conditions. If they don't, you've made a mistake. If they do satisfy the boundary conditions, if in fact your answers are self-consistent, almost certainly you have the right answer. It's very difficult to go through and do the procedure correctly do the procedure incorrectly and get an answer that will satisfy the boundary conditions. Now, the only problem would be if you apply the wrong boundary conditions. You're going to find a solution that is consistent with the incorrect boundary conditions that you applied. But algebraically, once you apply boundary conditions and find the solution, you can always plug them back in and find that your answer is self-consistent or not. And if it's not, then you need to go back and find your error. So let's do that now. We're going to go through and take our total voltage for the first transmission line, evaluate Z is equal to 0 at the interface, and we get this result. Likewise, for the total current, we get this result here. We do the same thing for our second transmission line. Evaluate the total voltage, which is simply the plus wave voltage at Z is equal to 0. And the current, likewise, we can determine, and we get these results. Our last step then is to see if these results verify our boundary conditions. And our boundary conditions from KVL say that the voltage at the end of the first transmission line must be equal to the voltage at the beginning of the second. And when we compare these two, we find we get exactly the same answer in both cases. Likewise, from KCL, the current at the end of the first transmission line must be equal to the current at the beginning of the second. And in each case we found we got the same result, and therefore it satisfies our boundary conditions. This again simply says that we have not made a mistake in our algebra, that our results are self-consistent. We started with boundary conditions and found the values that met those boundary conditions, at least algebraically. It appeared to meet those conditions. We inserted those algebraic solutions back into our original equations and found indeed they were the results were consistent with our original boundary conditions. And so we can conclude that our analysis is correct. And again, this is generally the case. And I have some minor frustration with students sometimes that will go through and apply boundary conditions and get an answer and then not go back and insert them in to see, in fact, if their answer is consistent with their original boundary conditions, to see if they've made an algebraic mistake. It's very easy, simple process to go through and do, and that's the great thing about the boundary conditions. You really can always tell whether you've done the correct mathematics, whether your answer is algebraically correct. It's easy to self-check, and in this case, it turns out we have done the analysis properly.